Who knows? Yeah, we're good.
Why don't you just click on start shooting?
No, it's already start shooting. It's on. I'm gonna start.
Yeah, we're just gonna crazy
Alright, so hope everyone got a chance to grab some pizza. Let's get right back into presentations. There is more pizza, so mid-presentation, if you guys want to grab some more, it's fine. Just try not to make too much noise. So next up, I'd like to call Ali Reza for his presentation on mixing services in cryptocurrencies. If I can get Ali Reza, that'd be great.
Thank you. So can everyone actually hear me? Let me. Sorry. So can everyone hear my voice well? Awesome. So hey everyone, I'm Ali Reza, master's student of computer science here at UW, and so I hope you enjoy your pizza and you can actually take a listen to my talk on mixing services and cryptocurrencies. And so these days I mostly work on LLMs, to be honest, not blockchains, but I have blockchains as a hobby, which is actually so interesting in my opinion. And so the steps that we're going to actually take in this presentation is first talking about background of what blockchain is and basically how transactions work in cryptocurrencies. So I assume that there is no need of having any prior knowledge on blockchains. And then we will go through mixing to see actually what the mixing is and also what is its relation with money laundering. And so let's get into blockchains. So let's talk about the main digital form of currency. So the main digital form that we right now use is credit cards, and the structure is in a way that we have a sender, and we have a receiver, and we have a bank as a third party to handle actually all of the transactions. And on the other hand, the structure of cash payment systems is in a way that basically governments and banks issue cashes, and the sender directly gives that to the receivers. So the bank do not perform any online transaction, and so they cannot trace the flow of funds. Basically, if you give cash to someone, basically no one knows that basically you made a transaction to them. So the main problem of credit cards is that they invade your payment privacy. Basically, governments and banks will know actually where you spend your money, what you buy, and they can trace everything. And so, invasion of privacy. And there's another problem that when the banks have complete control on all people's assets, so they will have the complete control on the economy of the society. And so sometimes it has bad results, like the USA 2008 financial crisis. Maybe you've heard about it. In a way that various banks went bankrupt due to offering some risky loans on the housing markets. And so what the government did was issuing 700 billion bailout program by using the people's money to help all the banks to prevent them from being bankrupt. So, and at that time, people realized that, so why should the government use our own money, the people's money, the money that actually we paid for the taxes and this kind of stuff to help these banks who went bankrupt because of their own fault. So why this should happen? So a cure to this problem was cryptocurrencies, a currency powered by blockchains, which is decentralized, so there's no centralized authority that can actually control the assets, which is also anonymous, means that your personal identity is not necessarily binded to the transactions, to addresses, and also there's no need to any third party. Basically, the third party is distributed in a decentralized manner, so you can perform payments online without being traced. So for example, if someone wants to buy drugs, so they can use crypto or cash without actually being traced. So Bitcoin was somehow the first cryptocurrency born in 2008 by by a random guy called Satoshi Nakamoto. And the key points of the proposal was actually the structure of transactions, the blockchain systems, and the financial incentive of miners. They stated that why miners should come to the actual Bitcoin ecosystem to actually do mining and receive some profits. No worries. And yeah, so let's go through the basic concepts of blockchain, just as a quick recap. So we can consider blockchains as a linked list in which it has some blocks. And so in each block, we have data, and we have the hash of the data, and we store the hash of the previous block, right? So the data inside of the actual blockchains, I'm talking about Bitcoin. The most important thing inside of the data part is transactions from an address to another address within a specified amount. And also, we store the hash of each block inside of itself. So a hash is somehow the unique identifier of each block. And we have the hash of the previous blocks to make that chain. Basically, the hash of the previous block works as a pointer to the previous block. So this is our linked list, in which we actually store the data of transactions and also the hash as a pointer inside of that. And so we can see actually saving this figure too. So basically, in the blockchain setting, we store all the transactions inside of the blocks, and all of them are publicly available for anyone to see. So it's observable to anyone, and it's transparent. It means that so all of us can actually go search through the internet to see the Bitcoin transactions and the Bitcoin blocks and see which addresses paid which addresses. So it's completely transparent. But there isn't any personal identity binded to these transactions. It's just some random bits of addresses. And so as I said, inside of each block, we store transactions like this. So just a quick point that we have to actually put in our mind is that in Bitcoin and most blockchains, we make transactions via addresses, not personal identities, right? So the question now is that, are addresses completely anonymous? Is using Bitcoin transactions enough for you to actually achieve the anonymity that you want? Does it actually prevent the governments from tracing your funds? See how it is. As I said, all transactions are public and visible to everyone. And so analyzing the transaction graph is completely possible by anyone. So if we actually plot the transactions graph, basically if we actually define each address as a node and each transaction as an edge, and then plot all of the actual transactions between different addresses, we will have a huge, huge complex graph. And so what can we do now here? We can perform many clustering-based algorithms, machine learning algorithms, and graphs, all the extensive literature that is available. So we can do it by your own. So basically, Bitcoin's public ledger is available to anyone. You can actually run any ML algorithm that you want to classify different addresses, to actually identify the different behavior of the addresses, to see actually, okay, gamblers make transactions like this. Drug dealers do that like this. So normal people do that like this. So it seems like the transactions are not fully anonymous. So basically it seems like a bank. It would be actually the same as a bank, to actually make all of the info of its transactions publicly available via the internet. But the only difference is that the name and personal identities are not binded to addresses. We use addresses as identifiers. So maybe it's not fully anonymous. Although we claim that, okay, we're using Bitcoin addresses, it's via the internet, so maybe it's not enough. And let's see. So as I said, we can analyze the Bitcoin transaction graphs. And so basically there are some tools that also you can use to actually see which addresses paid which addresses, to actually plot the different graphs, and actually find the relations between the behavior of addresses to real world users. And all of these tools are available online, like chain analysis that anyone can use. And also you can trace the flow of funds between different addresses to see from a specific address how much funds went to where. And as I said again, it's publicly available for anyone. And there is a place which these addresses will be binded to your personal identity. Centralized exchanges like Binance, Bybit, and this kind of stuff that you may have used. That they basically, the way centralized exchanges works is that you go to their website and you can actually convert your Bitcoin, Ethereum, or any cryptocurrency that you have to fiat currencies like US or Canadian dollars. But the issue is that they need your identity. When you want to sign up into these centralized exchanges like Binance, they want your name and family name, phone number, also your passport. Also, they require you to actually open your webcam to identify you, to make sure that your personal identity is completely correct. And so here is the place that your personal identity will be binded to those cryptographic addresses. And the government has access to it. And so, now the challenge is that how to convert crypto to cash when you don't want the government to actually observe you. Basically because we cannot use Bitcoin and Ethereum right now in the stores when shopping and these kind of stuff. At the end, we need fiat currencies to use, to be usable. And so maybe you've heard about the latest attack by North Korean hackers to one of these centralized exchanges called Bybit, which was $1.5 billion. That's too much. The net worth of this whole university, I mean the University of Waterloo, is $300 million. So it's 5 times more than the whole university that we have, right? So here the question is that, okay, these North Korean hackers stole that amount of money. How can they convert it to real world cashes? How to convert it to US dollar to be useful? And basically one of the most important source of funding for the North Korea is these kind of hacks. Basically, yeah, they pay their stuff by these hacking things that they do. And so, one other thing is that, this slide that I actually proposed here was published a month ago, on February 26th by actually FBI. And as you can see, as you can see, there are some addresses here. FBI announced these addresses as those ones which was used by the North Korean hackers to steal $1.5 billion. And so they said that, okay, any addresses which is connected to these ones is suspicious. And so if you make transactions to these addresses, or if you find that these addresses are binded to you, we will come up to you and see what's going on. So, but North Korean people know what to do, and there are some solutions to this, which is called as mixing. And let's see how they're right now laundering their money and convert it to cash. So basically mixing is the process that when we have several senders and each of them has some recipients, we want to have identity. We want to have entity here called as mixing service, which actually receive all of the funds of these senders, mix them all together, and then split them into their recipients. So this way, somehow an observer from outside cannot bind any senders directly to their recipients. For example, if you're actually an observer, we are seeing actually the transactions on the blockchain. So we cannot bind Alice directly to her actual recipient. So this is the process of mixing, right? To basically break the trace of the sender's recipient. So is it fine? Are we cool? Awesome. So let's see how we can do it. The basic thing, the simplest method to do is to perform swapping. So for example, we have 3 senders. We tell them, okay, so the first sender, instead of actually sending your fund to your recipient, send it to the recipient of one of the another senders. And so this is somehow like a simple permutation to somehow obfuscate the patterns, right? So it seems to be so straightforward and is used by many mixing services. Also, another cool thing, which is mostly used, is aggregating funds into a specific address, right? So consider that we have many senders here. One method to obfuscate the link between each sender to the recipient is to actually first put all of the funds into a specific address, and then in the next step, distribute that funds from that specific address to the recipients, right? So, is it clear that, so we aggregated all of the inputs into here, and then we are distributing the funds into the recipients. And so we cannot map each of these basically senders to their recipients here, because this big address do the obfuscation for us. Yes?
Can't you still track that? Like what's stopping people from tracking this kind? Or even the permutation? What's stopping people?
Track what?
Like you can still see the transaction.
Yeah, you can see them, but you cannot actually map the senders to their recipients directly. For example, consider that we have 100 senders here. 20 of them are drug dealers, 20 of them are gun dealers, and 60 of them are benign users. So here, we cannot actually discern whether actually in one specific address is for a drug dealer or for example, a benign user. We cannot map the recipients to the senders. That's the main goal of mixing.
Like that one drug dealer address, the way FBI issued those things.
Yeah.
Can't they see their transaction?
Yes, yes. So, for example, this address is for a drug dealer. So, who is its recipient? Maybe, for example, consider that I'm a drug dealer and want to buy drug from me. So, FBI actually flagged me as a drug dealer, and so you don't want yourself to be actually traced by FBI by actually making a direct transaction to my address. My address is flagged, right? So it wouldn't be good for you to actually directly send transactions to me, but the thing you can do is to use mixing. So I'm here. So we make the transaction to each other, and no one can directly map me to you.
It's still one of those options.
What do you mean by one of those options?
Like say that one person uses mixing service and they send to 20, the mixing service that has 20 recipients. FBI still knows it's one of those 20.
Yeah, one of those 20. That's right. One of those 20. But usually in these mixing services, there is not 20 people. There are 1,000 people. So one from the thousands of users. So what to do? It makes it so hard. And so yeah, basically the quality of mixing really depends on the number of participants in the mixing process. And so also if there is any question, please do not hesitate
Okay,
to
I
stop me.
have a question.
Yeah, sure.
Sorry. Is that service a third party or like an algorithm? Or
A very good question. Very good question. Yeah. There are several methods to do mixing. Some of them are centralized. Some of them are third parties that we have to trust them. Yeah, there is an entity. We have to trust them to do mixing for us. That's for a Bitcoin. But in the Ethereum, basically there are some things called smart contracts, in which there is a code who perform the whole mixing by itself on the blockchain. Now consider that there is a magical code, which is actually ran actually decentralized, in which all of the senders deposit their funds into it, and that works decentralized. That do the mixing and send the funds into the outputs. And so it can be both centralized and decentralized. But yeah, in many cases we have to, if our target service, our target mixing service that we want to use is centralized, so we have to trust them. And yeah, that may be an issue. Yeah. So also this is another figure that shows the exact previous thing. So consider that this one is 30. This is our address with 30 Bitcoins on it. So in each step, we send the sender's fund into the recipients. So first we have 30, so maybe the first sender wants to send 2 Bitcoins to their destination, so we do this. The next step, 2.5, 7.5, and blah, blah, blah. And as I said, the main goal is to obfuscate the linking between senders and receivers. This is our mantra. So also another thing that we can do is do cross-chain mixing. So consider that this is our Bitcoin blockchain. So don't be confused by these actually figures. So we have Alice. And so there is a mixing service. Alice tells the mixing service that, hey, I have, for example, 3 Bitcoin. So please, I will send it to you, the mixing service. So please send the equivalent amount in Ethereum to my destination. So this way, since the blockchains are different, there won't be any connection between the senders and receivers. But we have to trust that mixing service for sure. And so let's go back to the Bybit hackers. So they're now laundering their money. And so many researchers and actually companies are tracking their mixing procedure. And let's see how they work. And as I said, this is one of the largest crypto assets of all time. Basically not just in crypto. Basically the thing that happened just a month ago was perhaps the largest basically financial theft in the history. Basically, I think after that, the largest financial theft was from Saddam Hussein in Iraq, in which he stole $1 billion from their banks. So they beat them. Interesting. And so let's see how these North Korean guys are performing mixing. So they stole different kinds of assets. They stole Ethereum, Ether, Bitcoin, and various tokens on top of smart contracts. After this slide, and so the first step that they did was converting all the tokens, the tokens on top of smart contracts into the base crypto, the Ethereum. And the reason was that in some sort of smart contract tokens, the stakeholders of that can freeze their tokens. And so the first thing they did, just in a few minutes after performing that theft, was to converting all of the tokens into the base cryptos, Ether. And so they did that by using decentralized exchanges. In exchanges we have 2 formats, centralized and decentralized. They use decentralized exchanges for not being trapped, for sure, because of the problems that I mentioned about the centralized exchanges. And so we had a question.
In the previous slide, it was mentioned that that a great amount of money was stolen, but I've heard that the world was in debt to itself, we just don't have enough money. But where are they getting this funding from? Where are they? How?
Oh, how did they do that?
Yeah.
Basically, if you search about it, there are much explanation of how they did that. But yeah, it's fun. I can describe it, I think, in 1 or 2 minutes. Yes. So the basic thing they did was that they first identified the developers in top crypto exchanges like Binance, Bybit, and this kind of stuff. So, and they mailed the developers of those big companies, offered them some job positions with 5 or 6 times more salary. So consider that you are a developer in, for example, Binance or Bybit, and you receive an email that, hey, we are actually a new company, and so you're so good, you know your stuff very well, so we're offering you, I don't know, $1 million salary per month. So let's go to the interview. So, first, the interesting point was that those North Korean hackers first invited those developers to interview. So in the interview, they had a coding task. In their coding task, they had to download the base code, JavaScript code, to actually run it and do some coding on it. So the base code was completely okay. There wasn't any malware on it. But the issue was that there was a function there called update checksync. The update checksync function downloaded a Trojan, a virus. And so they did that to many developers, and they got access to their PC. And so consider that you have access to the PC of many developers in a company, in a crypto exchange. So maybe you can have access to some keys, some private public keys. You may have access to the ways to actually steal their payments, their assets, basically. You know, in all of these centralized exchanges, all of them has a database with access to all private key and public key of all people who actually gather their fund there. So they did that on many exchanges, and so they got by with, and so they stole 1.5 billion. Yeah.
Pretty sure for Bybit, it wasn't actually hackers like in the interviews, it was a supply chain attack. So like double check this, but I'm not
Sure,
pretty
sure.
sure. Is that for that case they had access to the software that they used to store their keys, and then it was a supply chain attack. So they actually made an update to the software that was automatically downloaded by these computers. It's a very rare case where it wasn't hackers that got into the company. It was actually a supply chain attack from a third-party software vendor. For that case, like that was a big point.
Yep. So let's just quickly review it to myself. So the code that the developers run, so it downloads a Trojan, and then
It wasn't a Trojan. It was so they used Trezor for their keys, like for their hardware wallets, right? And Trezor does updates regularly. They got access to Trezor servers, their AWS server, and they were able to make Trezor change the front end such that the front end was like spoofed. So it wasn't actually a Trojan on the developers' computers. It was the Trezor software server that got hacked, which made them change the spoof the front end. It's very unique, but that does happen, the North Korean thing. But for that case, it was actually people thought that was what happened, but they later learned that it was a supply chain attack.
Oh, I
Yeah.
see. Interesting. Yeah, thank you very much for fixing it. And so yeah, it was so basically a clever attack. Yeah.
So then how do I get into like mixing where they can send the money to my account? You know?
I didn't get it.
Like no, because you said like mixing is like how like they can send like money from one place to another without like being tracked. Like they should like send it to me. Like
Okay.
I'll make sure like the assets get sent to everyone else.
So basically, I showed you on a slide from FBI in which actually they pointed out some sort of Ethereum addresses for those North Korean attackers, right? So they want to actually somehow convert all of those assets into fiat currencies, USD. And so the aim of using mixing is that preventing the FBI from tracing them, using those aggregation, all of these methods. And so we'll go through it, that how they're actually performing it right now. So, are we cool? Yeah. So the mixing steps that they're right now currently performing is that first they spread their funds through actually various addresses. Knowing all of the cryptocurrencies, you can make arbitrary number of addresses and you can split your funds through all of them. And they're doing cross-chain swapping using decentralized exchanges. They're swapping their funds into various different crypto blockchains in order to actually hide the patterns. And also they're using mixers such as Tornado Cash and Crypto Mixer. And so the way that you can actually use, for example, Crypto Mixer, that if you go to their website, cryptomixer.io, so you will basically enter your destination address, you will set the time delay, you will set the service fee to actually gather the amount of security level that you want. And so it will do the mixing for you, and it is centralized. For example, this Crypto Mixer has been used since 2016, and it's centralized and people have trust on it. But if you ever want to use these crypto mixers, make sure not to do it on your Google Chrome. You should use Tor. Why? Because if you open your actually browser and type basically cryptomixer.io, the packets, the internet packets that are actually sent through the network has your own IP address. So yeah, the government can come and actually see that, okay, there is a user who made requests to the crypto mixer with this IP. So for example, they can actually track that, okay, you were from the University of Waterloo. So you will get them some clue. Kidding. And so this is a graph, and so we're not gonna actually extract any meaning from it. This is just a huge high-level graph that a tracing company called Elliptic showed of the North Korea's mixing procedure. This is a small subset of it, but it's just to actually show you that, yeah, when they want to perform mixing, they perform swapping, aggregation, all of these stuff many times to actually obfuscate the pattern. Yeah.
Are these mixers legal? Or?
Basically, mixing is a double-edged sword. On one hand, we can say, okay, it's good for actually enhancing the people's privacy, individuals' privacy. That was the mantra of basically cryptocurrencies like Bitcoin. But on the other hand, those are actually widely used for money laundering and illegal stuff, to be honest, at least in my opinion. And there isn't any certain rule to say that mixing is illegal, and there is nothing to say that it's legal. Basically, you can use it, but maybe if you use it for illegal activities, if the government identify that, then they actually come up to you and say, hey, what are we doing?
Because I don't know if this is like an assumption, but I feel like the government would probably want to make it where mixing is like on the legal side just because it benefits the rich people or like people that are like constantly having to make like transactions, because like I don't think an everyday person would be mixing generally, whereas like they would make it illegal so that money wouldn't be taken away as easily. You know?
Okay,
Because obviously
so consider that it's illegal. What do they want to do?
I mean, if
It's a decentralized thing, so
but I mean, would it still happen if it's illegal then?
it's not considered as illegal right now, but it's a decentralized thing. We can say that, okay, using Bitcoin and cryptocurrencies are also illegal because government can trace it actually easily. So mixing services are somehow the same with another extra layer of security.
Why do we let it happen then?
They can actually prevent people from using it. It's a decentralized thing,
Yeah.
like Bitcoin and crypto stuff. Yeah. So, yeah, awesome. And so this is my last slide about the game between cypherpunks and government. We consider cypherpunks as those who actually like to use actually Bitcoin, cryptocurrencies, and this kind of stuff. And on the other hand, we have the government. But so is it good for 9 people to have actually some systems like Bitcoin and crypto stuff, and also have the government to monitor the fundings and check whether actually money laundering happened or not? Basically, we need the government to actually make some rules for having actually, safe society. But on the other hand, we need privacy too. So in my opinion, basically it's a game theory challenge between these two agents. And at the end, I think it's good for us that we have the government to actually try to monitor different things to prevent criminal activities. And also we have the option to have our own privacy if we want. And so the question that whether the mixing services, cryptocurrencies, Bitcoin, Ethereum, all of these stuff are good or bad. So it's basically maybe an unsolved question. Everyone has their own opinion about it, but yeah, I think it would be interesting to think about it more and see whether it's good to use them or not. And yeah, thank you very much for your attention. So also if there is any more questions or sort of stuff, I'm available now and also after the presentation. So, sure. Hey, Mark.
So in the case of centralized users, it doesn't really make sense for any node creates to be because the risk of the government going to the operator of the centralized node and saying, hey, tell the operators to tell you what addresses non-trivial, right? Why does that have to happen? Not a security.
Yeah, basically, I don't know why. Basically, why North Korean people are using those centralized services, but that one, cryptomixer.io, is very well known since 2016, and many actually people have used it, and so maybe that's why they have trust on it. But also, it's interesting for me to know that, okay, why? Because those hackers know they work their job well. They know how to actually launder that amount of money. So, yep, I think it's still a question for me too. Yep. Elliptic, yeah. Sorry, typically is Repeat it louder. Yeah, basically that was just a graph. The transaction between different swapping aggregation and this kind of stuff, just in high level, without binding the senders or receivers, because they can't. Awesome. So yeah, thank you very much.
Alright, so that was a great presentation by Ali Rizzo about a very interesting topic in blockchain, especially considering the Biden attack just happened recently. So again, thank you very much. Next, we'll have Amit come up to do his presentation. Yeah.
Okay, testing. Do you hear me well? Okay. So my name is Amin and I'm a master's researcher and master's student researching blockchains. I've been working with blockchains almost for 4 years, and these 2 years, last 2 years, my focus has been on the scalability and interoperability of blockchains in general. And recently, I have been working on zero-knowledge proof-based solutions as well, which we will explore today. Okay, thanks to Alireza and Marco, we have an introduction on what blockchains are actually, and blockchains are decentralized systems that can't be controlled by any single entity, and they have different consensus mechanisms like proof of work and proof of stake to take care of securing a ledger that has the list of transactions and blocks, and at the end of the day storing a mapping that has address to accounting for like balance, code, and data if the blockchain supports smart contracts. And some blockchains, most of them support smart contracts, and even Bitcoin has some opcodes that can be executed on transactions, even though it doesn't support the smart contracts directly. And one of the most important features that we have is that blockchains are isolated from outside world, so they're not connected to internet directly. In smart contracts and transactions are completely isolated, which is a security feature actually. So we will first talk about scalability and the trilemma of scalability that we have. And as you can see in the diagram, we have decentralization, scalability, and security. And the trilemma explains that it's almost impossible for a single blockchain to satisfy all of these features at high quality. Although some recent efforts have been focused on providing these solutions, but if you check, you will see that they even slightly, they will sacrifice one of these features. For example, so let's define all of these words. So scalability is being able to handle the growing transaction rate while maintaining reasonable processing time and costs. So if the processing time is good but the cost goes high, then we consider the system not scalable. Security is the amount of resources that are required to corrupt the consensus and perform malformed transactions, double spending, or rewriting the history of blockchain. Decentralization is the number of validators that are participating in the network and actively validating blocks. So the higher the decentralization, the higher the security. So security and decentralization is actually two super correlated terms. And for example, for Bitcoin and Ethereum, we have this side of triangle, which they are super decentralized and super secure, but they're not scalable because their transaction per second rates are like 6 and 30 for each of them. And for other ecosystems, we have highly scalable and decentralized systems which are not super secure because of their consensus mechanisms. So security is about what does it take to break the consensus. For Bitcoin, which is a proof of work scheme, the entities should come together to form 51% attack. That means 51% hash power of the network to be able to override blocks or perform malicious actions. For BFT or proof of stake blockchains that are Byzantine fault tolerant, 1/3 of the network needs to get together and perform the attack. And another important factor is the total value locked and market capitalization of the blockchain. So the larger the market cap of a coin is, the more difficult it is to run these attacks, because like for a proof of stake blockchain, to perform the 1/3 attack, you need to hold 1/3 of the total value locked in the protocol, which could be billions of dollars, and that would not be efficient for a single entity to try and buy up all of these assets and try to override the validators. But if the chain is small and we have market capitalization of hundreds of millions, then one super wealthy individual can start buying up the market and start with their own validators to move away from the previous validator set and start acting maliciously. Decentralization is about number of validators and minimum cost for a user to become validator. So blockchains like Ethereum is trying to hold this feature by requiring not too high hardware costs for a validator and not too much of a stake for them to be able to participate in the network, and that's how it has hundreds of thousands of validators online. And another blockchains like Solana doesn't care about this feature, and their validators are actually, so Ethereum can be run on normal laptop with consumer hardware, but for example, for Solana, we have the requirements of the hardware is like 256 gigabytes of RAM, 64 cores of CPU that are high-end hardware and bare metal servers that normal user doesn't have access to. And another effort to quantify the decentralization of a blockchain is Nakamoto coefficient, which is defined as the minimum number of the validators or individuals that need to join forces to corrupt the consensus. For Bitcoin, this number is about 9,600 nodes, but the main issue here is how pools are affecting this factor. So in Bitcoin and other proof of work or proof of stake, we have concept of pools, which people get together to join their stakes or their hash power, their resources, to increase the chance of mining and getting rewards for them. And the problem with this scheme is that what if the pool can act maliciously on behalf of those users that are delegated to them and start making vulnerabilities to the security of the blockchain, which is a controversial topic and hasn't been solved yet. So for scalability, it's important to perform good under the load, and how it affects under load for processing speed and gas prices. Like for Ethereum, in the times of congestion, although the performance of blockchain doesn't drop, it still maintains the normal TPS, transaction per second rate, but the gas prices escalate to hundreds or thousands of dollars, which is not efficient, so the normal users can't actually do any transactions. So we need to identify which processes in blockchains systematically is becoming the bottleneck. So we have 4 core processes in a blockchain that runs through its entire lifetime to generate blocks. It's consensus. Consensus is to reach consensus on the new transactions that the system has got, and execution is executing those transactions in the virtual machine or whatever the blockchain uses. Settlement is settling on the current state of network and making sure everyone has the same state of network. And data availability is for having all of the data for transactions and latest data available for checking continuously. So solutions for solving this scalability try to solve at least one of these bottlenecks to make the system much more efficient. So we have direct layer 1 design changes, like rewriting the blockchain to support more transaction rate, be scalable, which we have sharding proposals for Ethereum, or modular designs like Cosmos SDK, or layer 2 solutions, which don't modify the layer 1, and instead they build a solution on top of the existing blockchain to inherit some of these parts, modules from that blockchain, but also try to achieve more scalability by offloading one of these features from the main chain. So layer 2 solutions are like payment channels, rollups, and validiums, which we will discuss rollups and validiums, but not payment channels. Payment channels are a super cool feature that are actively used in Bitcoin, and the idea is that two people can agree on some state of the world, and they transfer some money to one address, and the later transactions are done by just cryptographic signatures, and one can enforce that in times of disagreement. But if there's no disagreement, then you can have infinite transactions of chain, and finally when you decide on to withdraw your money, you would just claim those signatures on chain. So rollups and validiums are topics of interest for scaling the existing blockchains like Ethereum. So we have L1 blockchain here, which is producing the blocks. We built another L2 system that can be a blockchain too, but is usually a centralized sequencer that is trying to offload the execution part from the blockchain, from the layer 1 blockchain. So it gets the transactions from the users, batches them, and somehow efficiently submits it to the L1 blockchain after verification. So how the L1 blockchain makes sure that transactions that are submitted in batch are valid depends on the type of the system that is built. So for optimistic rollups, we have the assumption that we assume that the operator of the L2 is actually trustworthy and the blocks are correct. But we add like 7-day dispute period that if anyone detects any error, they can report it and the operator will be fined, and that reporter will be rewarded. So the security is via crypto-economic guarantees. And we will, in next slide, see ZK rollups or ZK validiums that actually cryptographically will try to prove the correctness of execution. So for interoperability, as I said earlier, blockchains are isolated from outside world. But what if we want to connect them to each other so the users of each blockchain can easily transfer assets to other blockchains? The reason for this is that different blockchains offer unique advantages, like Bitcoin has perfect security, or Ethereum, but their gas fees are high, and it may not be ideal for a user to do his transactions only on those blockchains, or like if some good opportunity is available on Solana, some coin that has been introduced, some user on Bitcoin may want to buy it, but without going through the centralized services. So that's why unlocking cross-chain functionality unlocks a lot of opportunities. There are different solutions for providing interoperability between different blockchains, and they're basically can be categorized in 3 ways, which one of them is notary-based, and light clients, which can be native or implemented in smart contracts, or cryptography primitive like hash time locks, which we won't discuss the cryptographic primitives because they're only for asset transfer and they cannot execute function calls, but are good for asset transfer. So bridges, notary-based bridges are bridges that there is a centralized or decentralized entity, bridge protocol, that is in the middle and watches the source blockchain for the user to lock his funds on source blockchain. So as long as the operators see the initiated transaction and the confirmation of lock, they would go forward and mint for you wrapped tokens on the destination chain, which you can spend. So the problem with this is that although source blockchain and destination blockchain might be secure, what happens if bridge operators that are notarizing these transactions are malicious or get hacked? If they hacked, the outcome is funds go boom. All of the funds are lost and the exchange will lose the collateral. So as you can see, the user locks his funds here, and the lock is actually the bridge protocol's smart contract or address. And in exchange, you receive wrapped tokens. Wrapped tokens is like the value is backed by this collateral. So if the bridge is hacked and all of the funds go from there to hacker's address, all of these wrapped tokens are worth nothing now. And as you can see, the biggest hacks, the Bybit is the recent one, which is through multi-sig phishing. But as you can see, we have Run and Bridge in the second place, which is private key compromisation, $600 million lost because the bridge operators' keys were leaked. And these hackers don't stop at anything, and they just try to hack all of this infrastructure. It's not the fact that these bridges were not secure, but relying on 3 or 4 keys for entire protocol will eventually be vulnerable to different attacks, or maybe even worse, the bridge operators may be malicious and they just wait for the right time to get all of the funds and just disappear. And as you can see, we have 1, 2, 3, 4, 5, 6 attacks out of these, about 10 attacks that are for private key compromisation. So, light client-based interoperability works on the fact that every blockchain has its unique block structure, and it usually has a Merkle root that has a proof of inclusion for all of the transactions in the block. So you could potentially verify that a transaction has happened in particular block without having the entire block, but just with the header. So if you have the block header, by checking the Merkle root, you can get a Merkle proof that verifies that particular transaction happened on particular block. So light client is a smart contract or a native program that lives on the target blockchain that actively monitors source blockchain's blocks. And this is usually happening by some relayers, because blockchains are disconnected. The relayers actually do the relaying of these headers. And if it's easy to verify if we have block n, if it's easy to verify the block n plus 1 by just having block n, then we can build a light client that just stores the headers and can easily prove that the transaction happened and the block got verified. An successful example of this is Cosmos Ecosystems IBC protocol, which has light client of chain B and A residing on each chain, so the counterparty chain's light client, and it builds some abstractions on top of that to provide connection that through channels, the applications and users can send data packets to the other chain and easily get verified. But this is for the case that the blockchain implements IBC, specific protocol, and it's usually handled by Cosmos SDK. So in order to support it, you usually have to implement your blockchain as Cosmos SDK. So these are blockchains that are looking like each other. Another example of light client solution is near Ethereum Bridge that is based on light clients, and it has core contracts similar to what happens in IBC, but this time in the smart contracts of each chain, and relaying the block headers here. The problem with this scheme is that because it's not native, it's actually expensive. So Near is a proof of stake blockchain that is cheap, and verifying the transactions that are coming from Ethereum to Near, relaying the block headers here, is actually easy and cheap. But for Ethereum, Near to Ethereum, verifying the signatures and blocks for Near is super expensive. I guess it's about hundreds of dollars, and because of that, this bridge latency is about 8 hours. So they gather all of the transactions and they only update the Ethereum core contracts 2 times a day. So they don't get bankrupt with fees. So we had an intro about zero-knowledge proofs. I will assume very simple black box, just a high-level abstraction that we have a private witness or input to a computation that we know a particular computation is occurring based on the circuit we have, or a program that is transferred to a circuit, and we will have outputs that are public and proof that this public is generated from a correct witness and correct computation. So how does zero-knowledge proofs help us in different ways? So in ZK rollups, we can offload the execution from the actual blockchain, layer 1 blockchain, to an off-chain service that gathers the transactions, the L2 blockchain that gathers the transactions and inputs the transactions to this program, which is EVM's equivalent. So it does the same processing that the execution layer on Ethereum would do. It would get the full block with the transactions and the pre-state of the network, and it would update the post-state and approve. So the proof can be easily verified, and as the witness is hidden, this proof can be super small, and the post-state can be simply a hash depending on the algorithm that the scheme is being implemented. So imagine this is a snark like ROS16 algorithm. It would be just, the proof would be just 200 bytes, easily verifiable in Ethereum with low cost. So we get the scalability by just using the ZK proofs and offloading computation, making sure that EVM was executed correctly, instead of optimistic solution that we assume it's correct and we wait 7 days to get the result back. So ZK Validiums are different kind of solution that does the roll-up, does the execution, same as roll-up, off-chain execution, but it also stores the data on somewhere else. So storing data on Ethereum is not cheap either. So we handle the problem of execution, and we are looking for a way to also offload the data availability to another chain or another data availability committee to make it more cheaper and faster to update and decrease the block time. So what happens is we could have another ZK program that validates the storage inclusion, like the operator could, after doing the execution, post the data, all of the new state or new transactions onto another blockchain like Celestia, which is, or EigenDA, which are specialized blockchains that are only used to provide data availability, and get that proof and verify that on Ethereum. So on Ethereum, we verify that the execution was correct and the data is available on a source that we actually trust. So we have offloaded the data availability and execution from L1, and we only have consensus and settlement left, which makes us derive the security from Ethereum and actually have a secure solution. So previous two solutions were for scalability, and for interoperability, we could have ZK bridges or ZK Lite clients, which some of them are actually operating now, and it's doing the same stuff that light clients were doing, but this time the light client verification happens inside the ZK program. So the purpose for this is that if the source chain and destination chain are different, significantly different, that verifying the signatures, verifying the block headers is not easy. Like for the Near and Ethereum case, that they wait 8 hours to cover the fees. Instead of that, they could easily do a ZK Lite client implementation of Near on Ethereum and verify that, which would cost like $1 or $2 instead of hundreds of dollars, so they could easily reduce the prices. All of this doesn't come with disadvantages, and let's go over the advantages first, which I highlighted most of them. So snarks are succinct. They're ECC based and they are usually small. As an example, Gross16 is 3-group element and 200 bytes. The disadvantage for Gross16 is that it doesn't have universal setup, and the trusted setup is actually a disadvantage of this algorithm. But other snarks exist that have, like Plonk, that have also a small size, a little bit bigger than Gross16, but they provide universal setup. Advances in ZK VMs, as Marco highlighted, allows arbitrary computation proofs. So you can pick an ISA, like RISC-V architecture, which has a lot of good tool chain available, and build your code into that and use a ZK VM just to prove that without actually knowing anything about circuits. So the ZK VM will take care of executing your RISC-V program and generating a circuit that can be used to generate a proof. Privacy is a side advantage of these solutions because we can keep the inputs hidden, and in certain schemes we can actually provide some additional privacy to what there is. And proof recursions are possible. For example, Snark can verify other Starks or Snark proofs, ZK proofs. So proof reuse is possible, and recursion makes it possible to divide the proof into different proofs. And this is actually the fact that makes it super parallelizable, because you can divide the computation and handle each computation trace in different devices like GPUs to make the proof faster. Disadvantages is that current solutions, most of them require strong infrastructure like GPUs. The last time I checked, actually, the benchmarks are not quite updated regularly, but RISC-Zero's ZK EVM implementation in RISC-V would take 30 minutes to prove a full Ethereum block, which is a lot actually, but compared to 8 hours and compared to rollup and the cost, it's actually a sufficient solution for now, but the advances like the pre-compose and the other parts are actually making this less and less every day. So proving can take minutes or hours based on the program we are proving and the inputs. And the main drawback we have is that all of these softwares are super new, and their beta stage and security of the ZK schemes themselves, and most importantly their implementation, should be assessed carefully, and most of these protocols haven't been audited carefully yet. Yeah, that's it. Thank you for listening. Yeah.
Any thoughts on L2 fragmentation, and also whether or not L2s are parasitic, or kind of whether or not they're a good thing for Ethereum?
I'm fan of L2s, but not the current state that we are in. So the fragmentation is actually not good, but efforts like the one that Polygon was taking, like unified contract, that would allow the different chains, L2s, to settle on the same contract. I guess that's a promising solution if it's implemented in a flexible way. that it could allow the settlement of different blockchains with certain requirements, certain L2s, to verify the zero knowledge proofs. So I guess it would unlock some good interoperability that users could switch fastly between L2s. But the current state, yeah, I agree that there's huge fragmentation, and L2s were mainly to scale Ethereum, but now they're stealing liquidity from it. And some of them are just promising some technological advances, but at the end of the day, they have a lot of training wheels, and their smart contracts can be overridden easily.